For a long time, accessibility of speech has focused on accurately capturing a speaker's words and displaying them with low latency. This is key. If captions are imprecise or laggy, the experience of users suffer, especially if they are deaf or hard of hearing. But precision and latency are not enough. Even when captions are accurate and fast, there can still be gaps between what a speaker is conveying and what captions are depicting. One such gap relates to how captions ignore non-speech information, or NSI. Non-lexical sounds such as incidental music, sound effects, ambient sounds, and of particular interest here, what we call extra speech information. Extra speech information includes all non-linguistic aspects of speech, such as speaker identity, tone, and vocal effect, among others. These elements are key in conveying a speaker's emotions, moods, and emphasis. We know that, for example, it makes a difference whether someone says something with a cheerful or cold voice, but these differences are not typically captured by traditional captioning systems. Prior work has found that at times this can lead to communication breakdowns, particularly when other cues are also missing. When a speaker's face is occluded, for instance, the absence of disambiguating facial expressions can make captions be perceived as ambiguous or even dull. To tackle this absence, one approach that has been explored involves using machine learning models to infer affective information from speech, embedding these inferred cues into the typography of captions. For instance, if someone says something that the AI model infers as having been said in a happy tone, we can represent those words with green colors. If the model infers anger, the same words can be shown in red. The speaker's arousal can also be shown as here through changes to the thickness of words. These two terms, valence and arousal, come from the circumplex model, a common approach in affective computing to map affective phenomena into values that can be represented along two continuous dimensions: valence, ranging from negative to positive, and arousal, ranging from calm to excited. A key challenge here relates to how valence seems to be easier for viewers to interpret visually than arousal. The use of color in particular has been shown an effective way of representing the valence of speech, i.e., whether it's positive, neutral, or negative. The dimension of arousal, however, has been shown to be more elusive, with a less successful representation through visuals. One alternative approach that has been explored involves using haptics as a complementary channel. While these past studies are still unclear as to whether haptics is actually understandable, its combination with visuals has been shown to improve engagement among deaf and hard of hearing viewers. But understanding is of course important. Perhaps part of the problem here is that psychology itself has competing accounts about what the concept of arousal means. At times, it seems to be either related to physiological or phenomenological phenomena, and some researchers have even argued that the term itself should be abandoned because of its ambiguity. All of this led us to ask, what is actually being conveyed to users when we encode AI-inferred arousal through typography and/or vibrations? In other words, and getting to the core question of this paper, when we say we are encoding arousal through haptics, what do people actually understand that to mean? How are the vibrations perceived in their relationship to emotions in a speaker's voice? We've explored this in a two-part study. Our first step involved investigating how deaf and hard of hearing viewers interpret arousal-driven haptic and typographic cues in captions. To look into this, we replicated the methods from our previous paper, Tactile Emotions, which proposed a speech processing pipeline that obtains arousal values for each word and conveys them through visuals and haptics. In practical terms, this meant that when participants watched videos using our system, high arousal was conveyed through strong vibrations and thick words, and low arousal through more subtle shakes and thin text. The vibrations were driven by a wrist-worn device similar to a smartwatch. In the experiment, participants watched a set of short clips that had this visual haptic setup. This was a large selection of videos that were diverse in speech style, genre, and speaker age and gender. After watching 48 clips, participants were asked how they typically infer arousal in conversation, which cues signal different levels of excitement or calmness, how confident they are in their interpretations, what makes a haptic pattern match an emotion, and which signals guided their interpretations. In summary, we were interested in the different dimensions of arousal in speech and how participants relate to this affective dimension. Through thematic analysis of responses from 17 deaf and hard of hearing participants, we found that there was no stable or shared understanding of the construct. Instead, participants drew on a wide range of cues to infer what the speaker was feeling: visual behavior, the semantic content of words, rhythm, and contrast in the haptic signal, and even contextual elements like the cinematic framing of a scene. Importantly, when we focused on haptics, many participants did associate stronger or denser vibrations with more emotion, which is how the AI model encoded arousal. But these mappings were far from consistent. Some participants interpreted stronger vibrations as meaning anger, others as loudness, and some even as narrative importance. This suggests that while arousal is itself a useful construct, it is difficult to pinpoint what it is actually meant to participants. For some, it mapped neatly onto haptics as more intensity equals more emotion. For others, it was interpreted more as contrast or salience over time. This heterogeneity suggests that arousal, made perceptible through haptics and typography, may be too conceptually fuzzy to support consistent interpretation. This motivated our second study, where we explored alternative mappings grounded directly in speech's acoustic structure. So at that point we ask, what if the problem is not in how haptics lends itself to interpretation, but rather to how it has been mapped to a concept that is itself fuzzy? So we deliberately stepped away from using AI to infer arousal and instead asked a more grounded question. What happens if we map speech directly to haptics without passing through an intermediate emotional label? Rather than using a speech emotion recognition model to infer arousal, we took a different approach. We extracted acoustic features directly from the speech signal, such as pitch, rhythm, and amplitude, and translated them into distinct vibrotactile patterns. The intuition here was that if listeners already rely on these acoustic cues to perceive emotion, then highlighting them through haptics may communicate affect without relying on the fuzzy and inconsistently understood construct of arousal. To do so, we developed 5 haptic patterns, each highlighting different properties of speech through distinct material qualities in the haptic signal. The idea was to explore how combining different haptic textures could form associations with different affective qualities of speech. In our experiments, participants experienced short, acted utterances expressing 4 discrete emotions: anger, happiness, sadness, and calmness. They then judged how well each of the 5 patterns matched those emotions. Our results revealed that no single mapping dominated across the 4 emotions, but some significant patterns emerged. The pulse pattern was more strongly associated with high-energy emotions such as anger and happiness. Pitch-normalized signals were more often associated with calmer states. Sawtooth textures were frequently linked to anger, suggesting the waveform roughness itself can carry affective meaning. Most importantly, these associations were not reducible to intensity alone. Participants responded to differences in rhythm, contrast, and what they described as the feel of the vibration. In other words, emotional interpretation seemed to arise from bundles of tactile features rather than from a single scalar dimension. This contradicts prior work which had been pointed to intensity as the most meaningful dimension of haptics. Taken together, the 2 parts of the study suggest a shift in perspective. Arousal-based mappings can improve engagement, but when arousal is implemented simply as more intensity, the signal becomes unstable and open to interpretation. Participants often read it as loudness, narrative emphasis, or importance rather than emotional intensity. By contrast, acoustic to haptic mappings grounded in the structure of speech produced rich, interpretable patterns. This does not mean that acoustic mappings are universally superior. Rather, it suggests that effective haptics could benefit from moving beyond single-parameter dials toward multi-parameter vocabularies that emphasize contrast, texture, and rhythm.